Modern backend have a simple problem: too many clients, too many endpoints, and not enough control. If every client talks directly to every service, you end up with a mess. No consistent authentication, no central place to log, no way to slow people down when traffic spikes. That's why API gateway and rate limiting exists. In this video, I will explain what an API gateway actually does, what rate limiting really is, and how they work together to stop your backend from melting down. Let's start with a picture. On the left, clients, browsers, mobile apps, third party integrations, internal tools, cron jobs, scripts. On the right, your backend services, authentication, billing, orders, search, notifications, analytics. In the middle, an API gateway. Clients send requests to the gateway, not directly to the services. The gateway is a single entry point that sits in front of your APIs. Its job is not to implement business logic. Its job is to handle cross-cutting concerns. Here are the things that every request should go through: authentication and authorization, rate limiting, routing, login and metrics, request and response transformations, and sometimes TLS termination. Instead of re-implementing these in every service, you put them in one layer. So what does the gateway actually do step by step? First, it terminates the connection from the client, usually HTTPS. It checks TLS, decodes the request, and can normalize details like headers. Second, it authenticates. For example, it validates an OAuth token, an API key, or a signed cookie. If the token is invalid, the request never reaches the backend service. Third, it authorizes. Optionally, it can check whether this token is allowed to hit this specific route. For some setups, that logic lives deeper in the app, but the gateway can enforce coarse-grained checks. Fourth, it applies rate limits and quotas. This is where we start protecting the system from overload or abuse. Fifth, it routes. Based on the path, method, or headers, it chooses a backend service. For example, API/users goes to the user service, payments goes to the billing service, and search goes to an internal search API. Finally, it forwards the request to the target service and later returns the response to the client. Along the way, it can log the request, add correlation IDs, and collect metrics like latency and error rates. All of that is the gateway. Now let's focus on rate limiting. Rate limiting is about controlling how many requests a client is allowed to make over a period of time. A simple rule might be each user can call this endpoint up to 100 times per minute. If a client stays under the limit, all good. If they go over, the gateway starts rejecting or delaying requests. There are three reasons to do this. First, protect your infrastructure. If one client floods you with traffic, they can make the system slow or unavailable for everyone else. Second, protect shared dependencies. Downstream services and databases can only handle so much load. Third, enforce fairness and pricing tiers. Free users get a small quota, paid users get larger limits. So, how does the gateway know who to limit? You choose an identity. For public APIs, that might be an API key or auth client ID. For user-facing apps, it might be a user ID or account ID derived from the auth token. For anonymous traffic, it might fall back to IP address, but that's less precise. The gateway tracks counts per identity and per rule. For example, 100 requests per minute to this endpoint per user, or 10 requests per second to this whole service per IP, or 10,000 requests per day across the entire API per API key. If a request would push the user over the limit, the gateway rejects it. The standard way to signal that is an HTTP 429 too many request response. You can also add headers that tell the client how many requests they have left or when the limit resets. Now, there's also the word throttling. Different teams use it differently. Sometimes rate limiting and throttling are used as synonyms. Sometimes people say rate limiting means blocking extra requests, throttling means slowing them down or queuing them. In practice, both are about controlling the flow. The important point is what behavior your system actually implements, not which word you pick. Under the hood, there are a few common algorithms used to implement rate limiting. One is a fixed window counter. For each identity, you count how many requests came in during the current time window, for example, 1 minute. If the count exceeds the limit, you block. It's simple to implement, but you can get bursts at the edges of windows. Another is a sliding window. You consider a moving window over the last 10 seconds or minutes, not aligned to the clock. This smooths things out but is more complex. Then there are token bucket or leaky bucket algorithm. You imagine a bucket of tokens that refill at a steady rate. Each request takes a token. If the bucket is empty, you reject or delay. These algorithms control average rate and allow short bursts. As an application developer, you usually don't implement these from scratch. Your gateway, reverse proxy, or API management platform provides them. Your job is to decide where to apply them and with what limits. Good patterns include per user limits on expensive endpoints, per IP limits at the edge to catch obvious abuse, global limits on critical dependencies, and software limits on non critical endpoints where you can degrade gracefully. Another thing to think about is where you place the gateway. Usually, it sits behind a load balancer. Clients hit a public DNS name. A load balancer spreads traffic across multiple gateway instances. Those gateway instances then route traffic to backend services that may themselves have load balancers in front of them. The gateway layer itself must be highly available because if it goes down, the whole API is down. So let's recap. An API gateway is the front door of your backend. It terminates connections, authenticates and authorizes, enforces rate limits, routes to services, and logs everything. Rate limiting is about controlling how often clients can call your APIs to protect the system and keep things fair. You don't need to memorize every algorithm. You do need to understand why these layers exist and how your endpoints behave when traffic spikes. If you design with that in mind, you will build APIs that survive both real users and stress tests.